Statistical concepts and market returns. This is a long reading with 10 sections. Essentially, we are going to focus on statistical methods which allow us to summarize return distributions. As investors, we are often concerned about returns on our investments and the distribution of those returns. And when evaluating return distributions, we are often looking for central tendency, which means the following. Let's say that the stock market has returned on average 14% over the last 10 years. Obviously, we are concerned with that average number. We are also concerned with dispersion, which tells us how spread out the data has been. One of the simplest measures of dispersion that we'll talk about is range. So, for example, if over the last 10 years, the stock market return has ranged between minus 20% and plus 35%, that is also important for us to know. Skewness talks about whether the data is skewed to the right, skewed to the left, or whether it is normal, which means that there is no skewness on either side. And then kurtosis is a slightly more difficult concept that we will talk about towards the end of this reading. All right, let's go over some fundamental concepts. First, the nature of statistics. And it is important to understand that statistics has two broad meanings. When we say, let's collect the statistics on XYZ, we are basically talking about data. So one meaning of statistics is essentially data. Another meaning is related to the methods that we use to collect and analyze data. And this is what we will focus on. When we talk about statistical methods, there are two subcategories. Descriptive statistics essentially describe the properties of a large data set. The mean or average return of 700 stocks in a given stock market, for example, would be a descriptive statistic. This reading is going to focus on descriptive statistics. Inferential statistics use a sample from a population to make a probabilistic statement about the characteristics of a population. In other words, if we have a population that is too large to analyze and we pull a sample out of this population and use the data in the sample to make an inference about the population, then those techniques are referred to as inferential statistics. And this material will be covered in a later reading. Let's cover some basic definitions that will be used in this reading as well as in subsequent readings. A population refers to all members of a specific group. So, for example, if you define a population as follows: all the publicly traded stocks in a given country, for example, could be a population. So, let's say that that number for a given country is 2000. A parameter describes the characteristics of a population, and generally this is denoted by the Greek symbol mu. So the average return of these 2000 stocks might be 10%. So we will say that the parameter mu, which describes the average return of the population of stocks, is 10%. A sample is a subset which is drawn from this population. Let's say we draw a sample with a size of 30, generally denoted by n. A sample statistic describes the characteristic of a sample, and this generally is denoted by x bar. X bar would be the average return of the 30 stocks in the sample, and x bar is called a sample statistic. Let us now talk about 4 different measurement scales. A nominal scale is one where we essentially only use names. A nominal scale is one where only names make sense. So for example, if we talk about different kinds of mutual funds, you might have a money market mutual fund, you might have a stock fund which focuses on growth stocks, you might have a stock fund or equity fund that focuses on value stocks. So notice that these three different funds are not better or worse relative to each other, and essentially only the names make sense because the names are telling us what sort of a fund we are considering. In an ordinal scale, the order makes sense. And a simple example would be the following. If we look at all the stock based or equity based mutual funds in a given economy, then you might say that here is the first quartile. So these are the funds that performed the best. Then second quartile, third quartile, and fourth quartile. So when we categorize and say that a given category is better than a second category, which in turn is better than a third category, then this is a ordinal scale. In an ordinal scale, the order makes sense, but we cannot say that this fund or this group of funds is better than this group of funds by X amount, and the interval between this and this is not necessarily X. The point being that while the order makes sense, there is no concept of a equal interval between the different categories. With the interval scale, however, not only do we have an order, but the interval also makes sense. The classic example of an interval scale would be temperature. If you have a temperature of 1 degree centigrade versus 2 degrees centigrade and 3 degree centigrade, we know that 3 is hotter than 2, 2 is hotter than 1, and the difference or the interval between the two makes sense. So if this is a 1 degree difference, the difference between 2 and 1 is also a 1 degree difference. So the interval makes sense. However, ratio doesn't make sense here. We can't say that 2 degrees centigrade is twice as hot as 1 degree centigrade. And finally, the most precise measure is the ratio scale, where we have order, intervals make sense, and the ratio also makes sense. The classic example would be the earnings per share of a given company. Let's say that earnings per share are $2 in the first quarter, and then in the second quarter the earnings per share are $4. We can say that in the second quarter the earnings were 2 times more than the earnings in the first quarter. With the ratio scale, there will also be an absolute zero. So EPS of 0 actually makes sense. This means the absence of any earnings, and then you can also have negative earnings. So in a ratio scale, there will be an absolute zero. Notice that with interval scales, there generally won't be a absolute zero, in the sense that while we do have a 0 degree centigrade, 0 degree centigrade does not mean the absence of temperature. Let us work through this practice question. We need to state the scale of measurement for each of the following. The credit rating for a corporate bond. As you will study later, corporate bonds have a credit rating which is an indication of their probability of defaulting and so on. The best credit rating would be AAA, which is better than a AA rating, and then lower ratings would be BBB and so on. Now notice that the order makes sense because AAA rating is better than AA rating, which would be better than a rating, but we can't say much about the interval. So this would be a ordinal scale where the order makes sense. Next, coupon rate. Bonds often pay a certain amount of coupon expressed as a rate. If a given bond pays a 8% coupon versus another bond that pays 6% coupon, you might also have zero coupon bonds. So notice that this is a ratio scale because we have an absolute zero, and if there is a bond which pays 4%, then we can say that this bond is paying a coupon that is twice that of this bond. Mutual fund classification types. If you have a fund that's classified as a growth fund versus another that's classified as a value fund, this is a nominal scale where only the name makes sense. We can't say that this is better than that or that a value fund is better than a growth fund, but the classification or categorization here essentially is just identifying two different kinds of funds. Name makes sense. This then is a nominal scale, and the easy way to remember this is N for nominal and N for name. And finally, bond maturity. You might have a bond that matures in 5 years, another bond that matures in 10 years. We can say that the bond that matures in 10 years has a maturity that is 2 times that of this bond. You can also have a bond that would be maturing very, very soon. So the maturity there would be practically zero. And therefore, this would also be a ratio scale. Summarizing data using frequency distribution. Let's say we have the summary data for 100 stocks with prices ranging between 46 and 65, and we want to organize and categorize this data. So what we do is divide the stock price into 4 intervals of 5 each, and then we figure out how many stocks fall within each interval. And we notice that 25 stocks fall in the 46 to 50 interval, 35 in the 51 to 55 interval, and so on. So this number is called the absolute frequency. In other words, 25 stocks show up in this interval, 35 in this interval, and so on. Cumulative frequency refers to the total number of stocks that have a price of 50 or less. So that's 25 over here. The total number of stocks with a price of 55 or less would be 25 plus 35, which is 60. The total number of stocks, or the cumulative number of stocks with a price of 60 or less, would be 25 plus 35 plus 29, which is 89. And then the total number of stocks with a price of 65 or less would be 100. That is called cumulative, and cumulative because we are essentially accumulating the number of stocks in each interval. Relative frequency simply says how many stocks we have in each interval relative to the total number of stocks. Given that we have 100 stocks and 25 are in the first interval, the relative frequency is 25 over 100, which is 0.25, and these numbers should make sense. Cumulative relative frequency is simply taking the cumulative frequency and dividing by 100. So here the cumulative frequency is 89, divided by 100 is 0.89. Now that you have understood what we've done here, the formal process for constructing a frequency distribution should be fairly obvious. Essentially, we first define the intervals, which is what we did over here. Then we tally the observations and count the observations in each interval. Here is a sort of question that you might get on the exam. Let's see if you can solve it. The correct answer is A, and you can read the explanation. Here is another question. Let's see if you can do this. The correct answer is C, and again just go through the explanation. Moving now to the graphical presentation of data. One of the most common ways of presenting data is in the form of a histogram, which is simply a bar chart of data that has been grouped into a frequency distribution. In other words, a histogram is a graphical representation of the frequency distribution that we just saw. What you are looking at over here is a histogram of S&P 500 monthly total returns between 1926 and 2002. In case you don't know, the S&P 500 is a major index in the United States. So what is this histogram telling us? It is essentially telling us, if we see these different return intervals, return interval of 2% to 4% is given over here. Then we have this as 4 to 6%, 6 to 8%, and so on. So returns have been broken into different intervals of 2%. And then we are looking at the number of months where the return fell in a given interval. So what this is saying is that in approximately 180 months between 1926 and 2009, the return was between 2% and 4%. And then if you look at this number over here, let's say this is about 150. In about 150 months, the return was between 4% and 6%. Notice that the histogram gives us a very quick sense of where most of the data lies. And that is the big advantage of presenting data graphically, in that you can quickly see how the data is distributed. A frequency polygon simply takes the midpoints of the histogram and connects those points. So if you take this histogram and the midpoints for each one of these bars and connect those midpoints, you have what is called a frequency polygon. The x-axis will have the midpoint of each of the intervals. So the 2% to 4%, which was shown right here, instead of giving the whole range, we will just specify the midpoint, which is 3%, and the frequency will be shown as a midpoint. So notice the 3% is shown right here and the midpoint is 180. Let's now look at the cumulative absolute frequency. We've already studied what cumulative absolute frequency means. This is simply the graphical depiction. And to help you interpret what you are looking at here, I will present a question. Let's say that we look at this 4% number over here, and I tell you that 4% over here reads off at 650. So how do we interpret this? The way we can interpret this is, in 650 months, the return, the monthly return was 4% or less. If with 0 we read off 400, what that would mean is in 400 months the return was 0% or less than that. And then what this would mean is that in approximately, let's say this reads off at 890, in 890 months the return was 24% or less. The cumulative frequency distribution will level off eventually at the total number of months. So if we take an extreme case of 100%, then obviously the number of months in which the return was 100% or less will be equal to the total number of months in our measurement period. And then after that, whether we pick 150%, the number of months with returns of 150% or less will simply stay the same. Let's look at a few practice questions. Here the correct answer is C. Here the correct answer is A. This is a little more difficult. Pause the video and make sure you do this before you move on. Here is the solution. What we have done here is shown the long way of solving the problem, where you come up with the relative frequency for each interval, and then the question is, what is the cumulative relative frequency for this interval? And what we then need to do is take all these numbers and add them up, which is done right here. So the cumulative relative frequency is 83.33%. A faster way of doing this would be to recognize that we just have one interval left after this, and if in that final interval we have 16.67% of the data, then before 16.67% we must have 100 minus this. So the quick way of doing it would be to identify 16.67%, do 100 minus that, which would give us 83.33%. So the way we can express this in plain English is saying that 83.33% of the data is less than 12. Measures of central tendency. And here are the different measures of central tendency that we will talk about. The arithmetic mean is the simplest measure of central tendency, and we arrive at the arithmetic mean by adding all the observations and then dividing by the number of observations. The arithmetic mean for a population is generally denoted by the Greek symbol mu, and this is your summation sign. So if you have n observations, you say I goes from 1 to n, and essentially you are summing up all the observations over here and then dividing by the number of observations. A sample mean is generally denoted by x bar, and here again the method is exactly the same. You go from 1 to n, so you sum up all the observations in the sample and then divide by the number of observations in the sample. The median is the middle item of a set of items that has been sorted into ascending order. Let's say you have these numbers which have already been sorted in ascending order. The median is the middle number. If you have an odd number, then this is straightforward. If you have an even number of items, then you take the middle two numbers, which in this case would be 9 and 10, and you simply then take the average of the middle two numbers. Note that the median is less affected by extreme values than the mean. To give you a simple example, if you have these numbers 7, 8 and 20, and this looks like a extreme value, the median over here is going to be 8. It is not overly impacted by the 20. If you have lots of outliers, then obviously the median can be impacted, but in this example 20 is not impacting the median. But 20 will have a major impact on the mean, because the mean over here is going to be 7 plus 8 plus 20 divided by 3. So because of this 20, the mean number or the average number will go up a lot. The mode is simply the most frequently occurring value in a distribution. In this simple set, the mode is 8. We can sometimes have data sets with more than one mode. They are called bimodal if there are two modes, or trimodal if there are three modes. It is also possible that a data set might not have any mode. Let's talk about a few other concepts of mean, starting with the weighted mean. In a weighted mean, different observations are given different proportional influence on the mean. Let's consider the following situation. You have invested in 3 stocks, and here is the amount that you've invested. Over the year, the returns were as follows: 5% on A, 7% on B, and 9% on C. And the question is, what was your portfolio return? If you simply take the mean of 5, 7, and 9, you would get an answer of 7%. But is that really an indication of how your portfolio has performed? The answer is it is not, because clearly a higher weightage of your portfolio is in stock C. Therefore, the return on stock C should have a larger bearing on the mean compared to the return on stock A. So how do we do that? Essentially, we do the following. We figure out the weightage of each stock. So the weightage of stock A is 40 divided by the total portfolio, which is 200 million. So A's weightage is 40 over 200. And then this needs to be multiplied by the return on A, which is 5%, plus the weightage of stock B, which is 60 over 200, multiplied by the return on B, which is 7%, plus the weightage of C, which is 100 over 200 multiplied by 9%. And then you simply solve this to get your weighted average. And intuitively, you should be able to tell that the weighted mean or the weighted average should be greater than 7% because of the higher influence of stock C, which has the greatest weightage of the 3 stocks. If you do the calculation, you should get 7.6%. And again, notice that the highest weightage of 0.5 comes from stock C. Now, a relatively straightforward point that you might not have thought about is that with your regular mean, each observation is given the same weightage. So what we do with the regular mean is say 5 plus 7 plus 9 divided by 3, which is essentially the same as saying 1/3 into 5 plus 1/3 into 7 plus 1/3 into 9. So 1 over n is the weightage given to all 3 items, and that clearly does not make sense in this situation. And just to emphasize the point, with a weighted mean, we put a weightage that is more relevant given the problem that we are solving. Now you need to try and solve this problem to make sure you understand how to calculate the weighted mean. This is the calculation, and the answer should be 2.44%. Let's now talk about the geometric mean, and we have seen this briefly in the previous reading also. Mathematically, the geometric mean of n numbers is simply a product of the n numbers raised to the power of 1 over n. So if you have 3 numbers, 7, 8, and 9, the geometric mean would be 7 times 8 times 9 raised to the power of 1 over 3, 3 because we have 3 numbers. The geometric mean is frequently used to average rates of change over time or to compute growth rate of a variable. If you think about it, interest rate tells us about the rate of change of money over time. So very often, to compute your average interest rate over a given year, we use the geometric mean, and that is what we did when we computed the time weighted rate of return in the previous reading. Let us look at a simple example. An investment account had returns of 20%, 20%, and minus 40% over the last 3 years. What is the arithmetic mean, and then what is the geometric mean? I'm asking you to calculate the arithmetic mean first, just to illustrate a point. If you calculate the arithmetic mean, you will have 20 plus 20 minus 40 divided by 0. So you will simply get an arithmetic mean of 0. But is that really what is happening? If you think about it, let's say you invest $100. At the end of 1 year, this will become 120. At the end of 2 years, that becomes 144. And then we have a minus 40% return in the 30 year, and we end up with only 86.4. So effectively, we have gone from 100 down to 86.4. So clearly, every year the return is negative. On average, how much did we lose every year? That is what the geometric mean will tell us. And the way we solve this is, we look at the return for the first year, which is 20%. So we put in 1 plus 20%, or 1 plus 0.2, which is 1.2, multiplied by, again, this 20% return over here. So we write 1.2 times 0.6 raised to the power of 1 over 3. And this should give us 0.9524. The interpretation is that for every year, on average, $1 is going down to $0.9524. And if you subtract 1, that means that your return on average for every year is minus 0.0476, which is the same as minus 4.76%. So this is our geometric mean return. If you look at the formula, here is what we've done. And again, this should be exactly the same as what you saw earlier with time-weighted rate of return. 1 plus R1, which is 1 plus the return for the first year, times 1 plus R2. And here we only have 3 years. So 1 plus the return in the third year, which is minus 0.4. And that in our calculation, or in our example, is 0.6 raised to the power of 1 over n, which is 1 over 3 minus 1. That gives us this number. Now, to understand this point, notice that if you start with $100, and then every year, if you are to lose 4.76%, so you lose 4.76% in the first year, lose 4.76% in the second year, lose 4.76 in the third year, then you will end up with 86.4. So the interpretation of the geometric mean is that it is telling you on average how much you are losing every year. To make sure you understand this concept well, do this problem now. You should calculate the return for the first year, the second year, and then simply come up with the geometric mean. 0.5 simply is 1 over 2 because we have 2 periods. We minus 1 to come up with the return. You should get 0.1832, which is 18.32%. Next, we talk about the harmonic mean. The harmonic mean is a special type of weighted mean in which the observation's weight is inversely proportional to its magnitude. This might be a little difficult to understand, but let's look at an example, and after the example it will make sense. Let's say you purchase $2,000 worth of your company stock every month. The purchase price over the last 3 months has been 20, 24 and 30. On average, how much did you pay per share? Now, the average amount that you pay per share is actually the harmonic mean. Let us just do this logically, and then I will show you how our calculation actually corresponds to this definition and this formula. To calculate the average price that you paid, what you need to do is figure out the total amount that you paid and then divide that by the total number of stocks that you purchased. You made a purchase of $2,000 worth of stock every month for 3 months. So overall you purchased 6,000 worth of stocks, which is essentially 2,000 multiplied by 3. Then if you look at how many stocks you bought in the first month, you bought 2000 divided by 20 because that was the share price initially. And then in the second month, you bought 2000 divided by 24. And in the third month, you bought 2000 divided by 30. When you solve this, you should get the average price that you paid for stocks. The answer you should get is 24, and that is the harmonic mean. Now let's look at the formula. XH stands for the harmonic mean. This is given by N, which is the number of items, which is 3 in this case, divided by the summation of 1 over X. X being each of the items of which you are finding the harmonic mean. In our example, that's 20, 24 and 30. So the first 1 over X would be 1 over 20, and then we have 1 over 24, and then 1 over 30. So that is the formula. If you look at what you've done over here and apply some basic algebra, you can divide the numerator and denominator by 2000 and you will still have the same fraction. If you divide the numerator by 2000, this cancels out. If you divide the denominator by 2000, then we essentially have these 2000s cancelling out and we are just left with 1. Notice now that what you have here is exactly the same as the formula for the harmonic mean. So once you are convinced that this works, you don't need to go through this relatively long-winded exercise. You can simply plug in N, which is the number of items of which you are finding the harmonic mean, and then 1 over 20, where 20 is the first item, and so on. This should give you 24. Now, this definition might make sense where we say that the harmonic mean is a special type of weighted mean in which an observation's weight is inversely proportional to its magnitude. So what this is trying to say is expressed over here. I would not get too hung up on this definition. The more important point is to recognize the use of the harmonic mean, which is given over here. When you are spending an equal amount of money on stocks where the stock price is changing and you want to compute the average price that you are paying, then you have to compute the harmonic mean. So here is a practice question that will help reinforce this concept. You should be able to do it quite fast, and the answer is, on average, you pay $12 per stock. Let us now look at a comparison of the arithmetic mean, geometric mean, and harmonic mean. If returns are constant over time, then the three will be the same. So if you have 3 years and in all 3 years the return is 7%, then clearly the arithmetic mean is 7%. The geometric mean will be 1.07 into 1.07 into 1.07 raised to the power of 1 over 3 and then minus 1. That will also give you 7%. And if you do the harmonic mean calculation, you will get 7%. If returns are variable, then the arithmetic mean will be greater than the geometric mean, which is greater than the harmonic mean. Let's say our returns over the 3 years are 7%, 8%, and 9%. The arithmetic mean is clearly 8%. If you compute the geometric mean, it is going to be less than 8%, and the harmonic mean is going to be even less than that. The difference between the arithmetic mean and the geometric mean becomes more if the variability increases. In other words, if the returns are then 5%, 8%, and 11%, the difference between the arithmetic mean is actually going to increase from here to here. And you should do this at least once in your lifetime to convince yourself that this is indeed true, and then you should be able to answer the sorts of questions that might show up on this subject. Moving now to other measures of location. Say you have the following return data for 20 mutual funds, and the data has been organized for you in ascending order. So we have fund number 1, 2, 3 all the way to fund number 20, and we are given the return data. We can divide this data into quartiles, which means that the data is divided into quarters. If you have a total of 20 funds, then dividing into quarters means that in each bucket you have 20 divided by 4, which is equal to 5 funds. So this would be one quartile, this would be a second quartile, the third quartile, and the fourth quartile. Dividing into quintiles means that we divide into 5 different buckets. So 20 over 5 is equal to 4. So here we would have 1, 2, 3, and 4. This would be one quintile. 5 through 8 would be another quintile, and so on. Dividing into deciles means dividing into tenths. So with 20 numbers, dividing into tenths would mean 2, and then 3 and 4, 5 and 6, and so on. And finally, percentile means that the distribution is divided into hundredths or percents. Let us now understand the concept of location. Again, using the same data, at a given percentile y with n data points, in our example n is 20, and the data is sorted in ascending order, the location of a given observation is as follows. The location of y, let's say location of 10. This 10 is referring to the 10th percentile. So the 10th percentile is 20 plus 1. Where is the 20 coming from? 20 is the number of data points, plus 1 is simply part of the formula, into y, which is the percentile. Essentially, we are coming up with the location of the 10th percentile. So the assumption is that the data has been sorted in ascending order. So y is the percentile and 100 is part of the formula. So we get 2.1. This is saying that the location of the 10th percentile is 2.1. This is the formula given to you in the curriculum, and this is the formula used in standard statistics textbooks. So you need to learn the formula and learn how to use it. But recognize the fact that if your sample sizes are small, then this formula gives you an approximation. It becomes more precise as the sample size increases. And the way you can see that is, for the 10th percentile, our location should simply be 2. But because of this plus 1, we get the 2.1, which means that our answer is an approximation. This works when we have larger data sets, but on your exam, if you get a question related to location, then you should use this formula. Let us now work through a practice question. Consider this data set, and using the formula that we just talked about, you need to find the 75th percentile, the first quartile, and the 5th decile. Recognize that the first quartile is the same as the 25th percentile, and the 5th decile is the same as the 50th percentile. Here is what you need to do. First, arrange the data in ascending order. So this is what you will come up with. Then, for the 75th percentile, we need to come up with the location, which is given by the formula that you should have learnt by now. The location of the 75th percentile is n, that's the number of items in our data set, plus 1, which is part of the formula, multiply by 75th percentile over 100. So this tells us that the location of the 75th percentile is 9, and then you look at the 9th value, which is right here. So the value denoted by P, so P75 is 40. L tells us the location, which is 9, and P, or the 75th percentile, the actual value is 40. So simplistically we say that 75% of the data is over here, and this would be approximately 75% because we have a small data size. Next, location of the first quartile. So location of the first quartile, that is the 25th percentile, that is given by, again, n plus 1 and then the percentile divided by 100. This gives us 3, that's the location. And then when you look at the third item, that is 34. And similarly, you can come up with the location of the fifth decile, and then P50 is 36. Now let's understand the concept of linear interpolation. Linear interpolation is used when the location is not a whole number or not an integer. And in other words, the location then lies between the two closest numbers. Say we want to find the sixth decile, and using our formula we come up with 7.2. This is the location number for the 60th percentile, which is the same as the sixth decile. Now we don't have a whole number here, so we must use linear interpolation, which estimates an unknown value on the basis of two known values that surround it. In the above case, the seventh value is 37, that's right here. The eighth value is 39, and we are actually concerned with location 7.2. So the way you can look at this is as follows. So we have the seventh value, which is 37, the eighth value, which is 39. So we need to come to point 7.2. So that is going to be 20% of your way between here and here. So about 20% of 2, that is equal to 0.4. So this number here is 37.4. That is the number that we have for P60, 37.4.